that's not what I want to make bigger. All right, so exact analytical transient response characteristics for first and second order systems is the topic of this lecture. We're going to say, okay, there are we can figure out analytically what each of these values is for first and second order systems. We could do it analytically for other systems, but it will become very tiresome, and we will stop. So just these. So first order systems without zeros. So a first order system without zeros has transient response characteristics, or transient response is characterized by a time constant tau that appears in the total response as something times e to the minus t over tau plus something, right? And so this is the term that this is going to die out, right? It's going to damp out over time. In 3 time constants, the transient exponential has decayed such that in 3 time constants, whoa, this is edit there. Said the same thing twice. 3 tau, only 5% of the term remains. Okay, so if you go out 3 time constants, this term is 0.05. This e to the minus t over tau is 0.05. That's getting pretty small. In 5 time constants, less than 1% remains. So this term that governs the transient component of this response is disappearing. And we know in a number of time constants, so 3 time constants, we're getting pretty close. 5 time constants, we're real close. There is neither peak nor overshoot for this type of response, right? They're just exponential decays. So they don't peak, they don't go past, they don't overshoot. However, the rise time for the system is found by solving the differential equation, the first order differential equation, 3.2, with output variable y and input u and real constant k. It's easy to show that the solution to 3.2 is this, and you guys could do this in your sleep. You could solve this differential equation. For whatever reason, every character is now coming in nicely except for big parentheses. Don't understand why, but for whatever reason that is the case. Spent way too much time trying to figure that out. From which we discover, so we've got the solution, that the steady state value is, if you take the limit as time goes to infinity, you get the steady state value, and that's just k, right? Because this decaying exponential goes to 0, and you're just left with k times 1. Not bad. The rise time is, by definition, the duration of the time interval between so t1 and t2, such that y of t1 is 0.1 the steady state, and y of t2 is 0.9 times the steady state. The first of these yields that, okay, which is to say we plug in t1 and we say it has to equal 10% of the steady state, which is k, and we solve for t1. That gives us what t1 is. It's negative tau log of 0.9, which is approximately 0.1 time constants. Solving in an analogous fashion, for t2, we get that t2 is approximately 2.3026 tau. The interval then is t2 minus t1, which is approximately 2.2 tau. Oh, I brought in the wrong one of these. It has this stuff filled in. These are fill-ins. So the first order system rise time is actually, you can do a log property to get this expression that the rise time is tau times log of 9, okay, natural log of 9, which is approximately 2.2 time constants. often we'll just use 2.2 time constants, but since we solved it analytically, we might as well express that. The settling time, so we found the rise time. Notice that we derived the rise time explicitly in terms of time constant. So we know rise time and time constant is a relationship there, and we've solved for it now, which is nice. The settling time can be derived in a similar fashion, and we get that the settling time is negative tau times natural log of 0.02. 0.02 because of 2% as our band there, plus or minus 2%. And it turns out that's like 3.9 time constants. Sometimes we'll just use 4 time constants, but that's the settling time for a first order system. So we've been able to express the time constant, or the relationship between the settling time and the rise time and the time constant, which is going to be very useful when we start doing system design. But even more useful than first order ones are second order ones. So second order system transient responses are characterized by a natural frequency omega n and damping ratio zeta. It is helpful to recall the complex plane graphical representation of the pole zero plot for a second order system without zeros, which is shown in figure 3.2, which is back over here, unfortunately. And this is also not filled in. I put in the wrong one and it's all filled in for you guys. So my system is still being worked out with bugs here, but we see that if we put the poles, so this is a pole zero plot, we put the poles here in the complex plane, P1 and P2, then, and we've seen this before, this is all review, but the real component is negative zeta omega n, okay, and the imaginary component is the damped natural frequency, so, which is by definition the natural frequency times square root of 1 minus zeta squared. This radius is the natural frequency. So from the origin out to the pole, that's the natural frequency. And the angle here is the arc cosine of zeta. If we move along a circular arc, we stay at the same natural frequency, but we change the damping ratio. If we're on this arc from the real axis to the imaginary axis, then we're going from zeta equals 1 here to zeta equals 0 here, and greater, and then less than 0, zeta means it's unstable. Greater than 1 zeta means that it's on the real axis. You have poles on the real axis that can branch off there. That is our sort of graphical interpretation of the relationship between the pole location, damping ratio, and natural frequency, right? And we've used that in the past, but we're going to use it even more in control systems. That's going to become even more powerful for us. So so following a procedure very similar to that for first order systems, but harder because second order system, there's more stuff involved. We can drive the following transient response characteristics. Okay, so the rise time does not have an analytical solution in terms of omega n and zeta, unfortunately. However, Nice has developed this figure numerically. I didn't have a chance to do my own. This is actually a little bit tricky to derive. You can't solve for this in closed form, but you can numerically create this relationship. And it has the relationship between damping ratio and percent overshoot. Okay. Really useful. Oh, wait, I put the wrong one in, didn't I? I did. Guys, this isn't supposed to be the percent overshoot one. That one's easy. There's a nice formula for that. What I want is the one for the rise time. I'll send that out. It's my bad. It's in the Nice textbook, but I'll solve for it myself and make my own graphic. The way I should have done it instead of copied it and put it in here. Okay. The peak time has the following simple expression. So the peak time is pi divided by the damp natural frequency. So that's convenient. The percent overshoot is related directly to zeta as follows. So the percent overshoot is related to zeta here. So I solved it both ways. So you can either go from percent overshoot, or you can either get percent overshoot from zeta, or you can get zeta from the percent overshoot. Those are two very useful expressions we will use a lot. That's actually what this figure is here, but I prefer to just use the formulas because they're not that complicated. The other one we need the figure, or we need a lookup table, which is equivalent. Finally, the settling time can be expressed as 4 over zeta omega n. And let's review what zeta omega n is. So zeta omega n, in terms of this graphical representation, is the real axis value. So it's the real part of the poles, right? So the settling time gets larger or smaller if we have a larger zeta omega n. Smaller. Settling time gets smaller because our decay is happening faster. Okay. We talked a little bit about that before, but we didn't have the term settling time before. So as you move these poles to the left, they settle faster. If you move them to the right, they settle slower and slower and slower until you hit the imaginary axis, and then they never settle. And then if you go to the right, they anti-settle. They like explode, right? And that is that. So that's all that I had on these. I have a little bit of discussion of when we can approximate higher order systems as second order systems, and we'll talk about that next time. Thank you for sticking around extra. I know that bonus class time is not always what you're looking for out of your Wednesday, but I enjoy it.